And this may look a little different from the printable notes that you had. I hope I actually get something to click on. I don't know if I had the links exactly right. In fact, it may not look anything at all like what you had. I had to update this link, I think, since the last class period. Someone, I appreciate you calling my attention to the fact that it was just not, well, I think I had the two different links linked to the same page, and so I had to change this one. A few words before we go today about absolute value equations and inequalities in section 1.8. Absolute value, as we know, indicates the absolute value of a real number indicates the positive distance between that number and 0. Absolute value itself cannot be negative, but every real number has an absolute value. So we take the absolute value of 3, we get 3 because 3 is 3 units away from 0. We take the absolute value of negative 3, we also get 3 because negative 3 is 3 units from 0. It's just to the left of 0. And what's the absolute value of 0? It is 0. So some things we have to keep in mind when solving absolute value equations. What two numbers can you think of that have an absolute value of 5? Right. Just right off the bat, we know if I put a 5 inside those absolute value bars, that'll make that true. If I put a negative 5 inside those absolute value bars, that will also make that statement true. 5 has an absolute value of 5, negative 5 has an absolute value of 5. So we get two solutions there. Now, if we change the expression inside a little bit, we don't change the fact that what's inside the absolute value bars has to be either 5 or negative 5. X minus 2, if we can find an x that makes x minus 2 equal to 5, like 7, that'll make this true. 7 minus 2 is 5. The absolute value of 5 is 5. Or if we can find an x that makes x minus 2 equal to negative 5, this would also work. But it's not negative 7, right? Negative 3. So add 2, x could be 7. Add 2, x could be negative 3. So if we have the absolute value of some expression equal to a positive number, thing to do is just acknowledge that expression could be that positive number, and its absolute value would be that positive number, or that expression could be the opposite of that positive number. So we could very well say x minus 2 equals plus or minus 5 in a case like this. We get two solutions. And note that we're solving equations for the moment, so no interval notation, just the listing notation for describing these solution sets. B part, there's a little bit more going on, an extra step, I believe. C part and D part. Absolute value of negative 3x plus 7, that quantity, equals 5. That could happen. It could happen if negative 3x plus 7 equals 5. It could happen if negative 3x plus 7 equals negative 5, either way. And we just follow through and solve the individual equations to see what we get. On the one hand, it looks like, whoa, that's an equal sign there. It looks like x could be 2/3. That's a possibility. What is the other possibility? Is it 4? So we take 2/3 and substitute for x. Negative 3 times 2/3 is negative 6/3, which is negative 2. Negative 2 plus 7 is 5. If we take the absolute value of 5, we'll get 5. So 2/3 is good. If we go with 4, negative 3 times 4 is negative 12. Take negative 12 and add 7, what do we get? Negative 5, but it still has the right absolute value, because the absolute value of negative 5 is going to be 5. So 2/3 is good, 4 is good for this equation. Now the last one, this is the one where you get your test back and you groan. You think, why would he put one like that on the test? He's awful. And I don't remember if I put one like this on the test or not. Maybe I didn't. I hope I didn't, because it's just sad. What number can you think of that has an absolute value of negative 5? None. There's not one. There's not one. You pick an x, any x, multiply by negative 3, add 7, take the absolute value, you do not get negative 5. There is no solution to this equation. Now it looks like maybe you would take and do what you did with the C part, set it equal to 5, set it equal to negative 5, but to no avail. No number works here. It's just the empty set. Now, if you see this problem on the test and you realize, oh, there's a negative there on the right-hand side, I don't really have to do much work on this, I just write the empty set and keep going, then it's a happy thought, right? But if you don't recognize it, it's a lot of work for nothing. This is not behaving like the other PDFs. Example 2, I would expect one like this on the test, though. You've got absolute value of one quantity equal to an absolute value of another quantity. Let's just kind of look at this. Suppose I have the absolute value of this equal to the absolute value of that. Two ways this might be true. What's one of those ways?
Do the same thing that you would do previously. X minus. Do not. Not maybe want me to say.
Well, what's the relationship between this and that would make this a true statement?
That's the absolute value of this, and this is the absolute value of that.
Maybe. Maybe. If this or that, or maybe this and that, are positive, but maybe this or that are negative, so what might make this happen? Would this be true if this equals that? Would that be true?
Yeah.
If this and that are the same, then they have the same absolute value, right? They might both be positive, they might be both be negative, but if they're the same, then they have the same absolute value. Is it possible for two numbers to have the same absolute value even though they're actually different numbers? Well, you have negative 3 and you have 3. Do those two numbers have the same absolute value?
Yeah.
They do. They do. So two ways this is going to happen. It happens if this equals that, right? If this equals that, then the absolute value of this equals the absolute value of that. But the 3 and the negative 3, that relationship there, this is also true if this equals negative that. Yes, that's the other way it happens. So you have two quantities, they're exactly the same, they have exactly the same absolute value. Or you have two quantities that are opposites of each other. They also have the same absolute value. That's the realization I want you to embrace for this particular example. If you can embrace that realization, the two quantities can have the same absolute value two different ways. They could be the same or they could be opposites. Then this will go very well for all of us. So x minus 7 might equal x minus 5, but actually I don't think there's an x that makes that happen. Or x minus 7 could be the opposite of x minus 5. So just, they could be the same, they could be opposites. Either way, they have the same absolute value. First one, bad things happen. The x's go away. Minus x, plus 7, 0 equals 2. Not getting solutions out of that. But the other way we do, I think, x minus 7 equals negative x plus 5. If we add x to both sides and add 7 to both sides, I think 2x equals 12 is promising. Is 6 going to work here? What if we take 6 and substitute it for x on both sides? Does it make the equation true? 6 minus 7 is the absolute value of negative 1. 6 minus 5 is the absolute value of positive 1. Now, negative 1 does not equal 1, but they have the same absolute value. So that works. 1 minute and change. I think we can do this last one here. Or this next one here. It's not the last one. But it gets us close to the end. 2 minus 7 equals x minus 5. That's one possible way this could be true. What's the other possible way this could be true? It could be the opposite of x minus 5. Either way, the quantities have the same absolute value. They could be the same, or they could be opposites. So, subtract x, add 7, A little messy, but x equals 2 is a possibility. We'll check it in a moment, if we have a moment in a moment. I'm a little worried. Add x, add 7, 3x equals 12. Does 4 work? I have less than a minute to check it. Let's see. Let's try the 2. 2 times 2 is 4. 4 minus 7 is negative 3. 2 minus 5 is negative 3. This is a true statement. They both have an absolute value of 3. Let's check the 4. 2 times 4 is 8. 8 minus 7 is 1. 4 minus 5 is negative 1. Same absolute value. The statement works. So, 2 possibilities. This equals that, or this equals the opposite of that. Have a great couple of days. 1.8, and I think we did example 2. Because we talked about the absolute value of this equals the absolute value of that, and what the relationship this had to that. Example 3. Absolute value equation. Now this goes back, it's really more like example 1 than it is like example 2. But it's kind of souped up a little bit because it's got a quadratic expression on the inside. And it really emphasizes if we've got the absolute value of a quantity equal to a positive number, what really has to be true? Well, we've got some flexibility. That quantity could equal that positive number, or the quantity inside could be the opposite of that positive number. Either way, when we take the absolute value, it's going to be a true statement. So 2 possibilities. 2 possibilities. X squared minus 6x minus 4 could equal 12, or x squared minus 6x minus 4 could equal, what's the opposite of 12? Negative 12. Now, in a problem like this, when I'm grading it, I've got the test back and I'm grading it, and I don't see that on the paper. That's off somewhere. It's not even there. All I'm seeing is this. I have to think back, what's the purpose of putting this problem on the test in the first place? I want to get an answer to the question, does the student know what to do in case of absolute value showing up in an equation? Does the student know what to do in that case? Now, there are other problems on the test involving quadratic equations. I'm pretty confident the student probably successfully solved a quadratic equation like this, maybe even harder than this, earlier in the test, maybe by factoring, maybe using the quadratic formula, and I feel good about the student's quadratic equation solving skills. So I'm wondering if this is all I see, and from here it goes well, the student demonstrates the ability to solve a quadratic equation. Is that really making any steps toward answering the question in my mind, does the student know what to do in case of absolute value? And I'm thinking the answer is no. You think maybe there are going to be 4 solutions to this, ultimately. What if the student gets the solutions to this part, but doesn't even know that the other part exists? Is that half credit? What do you think? Is that half credit? In the past, in some cases, I've said, yeah, I guess, whoa. Maybe for emphasis, make it large print. I've said maybe half credit for that, but really, that credit has been obtained on a different problem. I know you can solve that quadratic equation. What I don't know is, do you realize that if the absolute value of a quantity equals 12, then maybe that quantity equals 12, or maybe that quantity equals negative 12. That's really what this problem is all about. If I can't get an answer to that question, I should leave this problem off the test. So the solutions that really are the money solutions, the ones you get the points for, are the solutions to this one. Now you need the other ones too. But I'm looking to see, can you write this statement? I mean, this statement really helps me to realize, yes, the student gets it. The student can take an absolute value equation and write an equivalent equation without the use of absolute value. And then I say, okay, if a little careless mistake occurs from here to the end, it's minor and wouldn't count off much. But if the or x squared minus 6x minus 4 equals negative 12 is not present, then I still have confidence in the student's mad quadratic equation solving skills. But I realize for this problem, the student does not get it and does not understand what the absolute value really means. So be sure to include the or. The expression could equal the negative of that. So here goes. We can do this. It should be easy for this to point out. X squared minus 6x minus 16 equals 0. Or x squared minus 6x. If we add 12 to both sides, what's that? Plus 8 equals 0. And it's pretty easy factoring. Hopefully I don't mess it up. X minus 8, x plus 2 on the left-hand side. And over here, x minus 4, x minus 2. That'll give us the negative 6x in the middle. X minus 8 equals 0, or x plus 2 equals 0. X minus 4 equals 0, or x minus 2 equals 0. X equals 8, or x equals negative 2, or x equals 4, or x equals 2. 4 solutions to this. If we don't have the absolute value, there are only 2. And I think the graph of this may kind of shed a little bit of light on what's really going on here. If you were solving this graphically and you did not have the absolute value bars, there would just be 2 solutions. Let's see if we can see what they are in a class period or two since I pulled out the graphing calculator. So first, without the absolute value, you'll have y equals x squared minus 6x minus 4. And then if you're using the intersection of graphs method, basically y equals the left-hand side, y equals the right-hand side, and the picture, I'm going to zoom 6. I think the standard viewing window is probably going to show us what we need to see. Actually, I'm completely wrong about that because y max is 10. In the standard viewing window, I've got to go as high as 12 if I'm going to see y equals 12. So I am going to zoom 6, but then I'm going to tweak the y max so it'll go as high enough so we see the y equals 12 there. There's the left-hand side. And then if I change the viewing window so the y max is maybe 15, and maybe a y scale of 5, graph it. Y equals the left-hand side, y equals the right-hand side. I don't think we have to do the second Calc 5 thing to find these, because you see the point right here, and you notice it has an x coordinate of -2. And that's from our solution, x equals -2 there. And you see the point right here, it has an x coordinate of evidently +8. These are the only 2 points of intersection, and so those are the only 2 solutions if there's no absolute value. But if there's absolute value, we've got to think, what is putting absolute value around that x squared minus 6x minus 4 going to do to the graph? Whatever's above the x-axis is not going to be changed. This portion right here is going to stay just like that when we graph y equals the absolute value of x squared minus 6x minus 4. And this right here is going to stay right there, because the absolute value of something that's positive is just that thing. But what's going to happen to the bottom portion of the graph, that which is below the x-axis when we take absolute value? Well, what do you get when you take the absolute value of a negative number? Well, just in general, what's the absolute value of -7? It's 7. So it's not the number we took the absolute value of, it's the opposite of that. So what it's going to do, we'll talk about reflections about the x-axis in section 2.6. I think that's where that happens. Whatever's below the x-axis is going to be reflected about the x-axis. It's going to take the stuff that's down here, and it's going to reflect it like that when we graph y equals the absolute value of the left-hand side. So now, in the past, I like most aspects of the new operating system. TI-83 plus users might have a little advantage here. You can just do second insert and actually put the ABS in front of this. I'm thinking, I don't know of a good option for TI-84 plus users here except to clear and press Math and press the right arrow. So Math button, right arrow to take you to ABS. And then if you press 1, TI-83 plus users are going to see ABS open parenthesis. TI-84 plus users are going to see absolute value bars. So then we retype. Since I don't believe the TI-84 plus has a copy and paste feature. If it did, I would take advantage of it. But I'll retype this. X squared minus 6x minus 4. I mean, there is the second entry, but even that I don't think would enable me to enclose something in absolute value bars. So if we graph it with the absolute value bars, we see this. Okay, it takes whatever was previously below the x-axis, reflects it about the x-axis, and we pick up 2 extra points of intersection. Those 2 extra points of intersection, evidently, this one right here has an x-coordinate of 2, for the 2 right there, and the other one has an x-coordinate of 4. So the 2 and the 4 we pick up simply because of the absolute value. So you want to know if it's the absolute value that we want to be 12 and not just the expression itself, then there are the 2 possibilities where the expression could be 12, but there are also the 2 possibilities where the expression could equal -12. So make sure that you rewrite it and consider all possibilities in a situation like this. That should just about take us to, that should just about take us to inequalities, yes. Absolute value inequalities. Again, the big key with these absolute value inequalities is to be able to take the expression that has an absolute value symbols in it and rewrite it as an equivalent expression, one that means exactly the same thing but doesn't have absolute value bars. The first step is really the most important step. From there, it's kind of easy because we've solved inequalities before without absolute value bars. So the big deal with these types of problems is, can we get it from the statement with the absolute value bars and answer the question, do we really know what this means? By writing it as an equivalent statement without the absolute value bars. Let's see. Let's start with something. This is a general absolute. It's supposed to be U there. Value inequalities. Let's think of some numbers. Real numbers, integers if we can, starting with integers, although we want to go beyond that to rational numbers that might not be integers and irrational numbers. The absolute value, sorry I'm not paying attention, now I am. Can you think of some numbers that have absolute value that have absolute value less than 4? And listen, 3. Yes, indeed. Beginning with 3, definitely a number that has absolute value less than 4. Can we think of some other integers that have absolute value less than 4? What's another one? I heard 0. 0 has an absolute value 0, and that's less than 4. Good. What are some more? 2. 2 has an absolute value of 2, and that's less than 4. A few more. 1. 1 has an absolute value of 1. That's less than 4. Is that all? Negative 2. Yes. Negative 2 has an absolute value of 2. That's less than 4. Negative 3 has an absolute value of 3. That's less than 4. Negative 1 has an absolute value of 1, and that's less than 4. Okay. Any other integers? No more integers. We can't go 4 or negative 4 because we don't have the or equal to bar. We certainly don't want to go 5 or negative 5 because they're too far from 0, right? Too far from 0 to have absolute value less than 4. Now we can expand this. Let's go beyond the integers to allow for rational numbers or irrational numbers that lie in between the integers, like 3.5. How about 3.5? 3.5 has an absolute value of 3.5, and that's less than 4. 3.9. Yeah? It has an absolute value of 3.9, and that's less than 4. 3.99999. Yeah? So we can push the envelope and get just as close to 4 as we please, provided we don't get to 4. So I'll put a parenthesis there. Alex might want an open circle there to indicate that that's the right-hand endpoint of the interval, but it's not included. How about negative 3.5? Negative 3.99999. Push it in the other direction. We can get as close to negative 4 as we please. As long as we don't step on negative 4, it's going to be okay. Shade everything in between. If we're trying to describe what portion of the real number line consists of numbers that have absolute value less than 4, it's this. Now, how would we describe this interval? We've got a graph. How would we describe it, let's say, with an inequality? If you want to run an inequality without absolute value bars, how do we describe this interval? Would it be enough to say x is less than 4?
Negative 4 is less than x, but x is less than 4.
We kind of need both. It's really two things. It's we can write it with an and. We could say negative 4 has to be less than x, and x has to be less than 4. Or we could put them together in the 3-part inequalities that we've looked at and use the word between. Between is a great word for describing these absolute value inequalities involving less than. X has to be between negative 4 and 4 if it's to have absolute value less than 4, because it's got to be less than 4 units away from 0. So x is between these two numbers. This is the big deal with these absolute value inequalities involving a less than. You want to take them, write it as an equivalent inequality without the absolute value bars. A 3-part inequality is the way to go if it's a less than. Now what changes? What changes? Let me see. Not a whole lot changes, so I'm just going to try to take advantage of the copy and paste feature. What changes if, okay, that's fine too. If we put All right. If we put the or equal to bar there, what's different?
Brackets.
Brackets, yeah. We pick up the 4 and we pick up the -4. So we use brackets instead of parentheses. And it's the or equal to bar and the or equal to bar. Just like that. Okay. Not a huge difference. So the huge difference that happens in this case is not whether there's an or equal to bar or whether there's not an or equal to bar. The huge difference is whether it's a less than, or we haven't done the greater than case, have we? Can you think of some numbers that have absolute value greater than 4? Integers to start with. 5, 6, 7, 8, 9, 10. So 5 definitely has absolute value greater than 4. 6 definitely has absolute value greater than 4. 7, 8, 9, 10, 11. Positive infinity. All the way to the right. Oh, absolutely. All the way to the right. Is that it? Well, decimals right in there. Is this all the integers that have absolute value greater than 4?
Could it be -5?
It could be -5, right? We would take -5 and take the absolute value of -5. We get 5. And that's greater than 4. So -5 definitely has absolute value greater than 4. What about -6? Sure. -6, -7, -8. Only requirement is that the number be more than 4 units away from 0. It could be more than 4 units to the right of 0. It could be more than 4 units to the left of 0. It can't be within 4 units of 0. So if we allow for non-integer rational numbers or irrational numbers, we can go 4.5, we can go 4.1, we can go 4.00001. That's all good. Anything greater than 4 is going to have absolute value greater than 4. What other numbers on the number line have absolute value greater than 4? How about anything less than -4? Those are also going to be good. So to take this statement, absolute value of x is greater than 4, and rewrite it as an equivalent statement without using absolute value bars, it's going to take 2 separate intervals. And the thing is, it would seem that if a 3-part inequality works well enough there, a 3-part inequality should work well enough here, but it really doesn't. It really doesn't. Yes?
I don't mean to jump ahead.
Oh.
I'm jumping ahead, so I'm sorry.
Mm-hmm.
When the absolute value is less than a number, is that like an and statement?
Mm-hmm. It is an and statement. It's -4 is less than x, and x is less than 4. It is exactly like an and statement.
If it's greater than, it would be an or. Is that correct?
Yes. X is less than -4, or x is greater than 4. That's like an or statement. It's exactly like an or statement. And the thing is, an and statement often translates nicely as a 3-part inequality, because an and statement can often be written as a single interval when you look and see what those 2 statements have in common. But an or statement almost never translates well as a 3-part inequality, because usually we get 2 separate intervals. And we're not saying it's everything in between 2 particular numbers. We're saying it's everything to the right of this one together with everything to the right of this one, and it just doesn't work well as a 3-part inequality. So it needs to be kept as an or statement like this, and bring it down, and ultimately we would have something like -infinity to -4 union 4 to positive infinity, and we'd write that as our final answer. Okay, so it just can't be written as a 3-part inequality. What changes if we allow for the or equal to bar? Brackets. That's the only change. If we put the or equal to bar, We pick up the negative 4. We pick up the positive 4. We have an or equal to there. We have an or equal to there. And we get brackets there and there. That's the only change. Now, we don't want to ignore that change, but it's not a real major change. It just affects the endpoints, having them versus not having them. The big difference between the solution sets is whether it's a less than a positive number or a greater than a positive number. That's huge. You want to be able to look at that, and if it's the absolute value greater than some positive number, that means one thing. If the absolute value is less than a positive number, that means a completely different thing. Let's look at some of these. And I can probably zoom on that a little bit. The absolute value of x is less than 7. Okay, this is not really much different from what we've done, but the key first step, we notice it's less than a positive number. So we're thinking if the number is less than 7 units away from 0, then it can't stray too far to the left or to the right from 0. So it's got to be in between, what two numbers? Negative 7 and 7. So we look at that. We just go through that little thought process and realize, okay, it's got to be between negative 7 and positive 7. So negative 7 is less than x is less than 7, and we've got it there. Now, we want to write our final answer. Didn't say here, but on the test I'll say, write your final answer using interval notation. So in interval notation, it's the open interval from negative 7 to 7. These are the numbers on the real number line that have absolute value less than 7. Now the B part, I hope the B part does not show up on the test. I almost feel bad. You know, I don't feel bad showing it to you in class, that I feel good. In the interest of full disclosure, what to do in case of a negative number on the right-hand side. It would seem like it's similar, but it's kind of different. No solution. There is no number that has an absolute value of negative 8 or negative 9 or negative 10 or negative 11 or anywhere close to negative 7. So nothing, no solutions to this at all. Just be on the lookout for something like that. Maybe it'll show up on the test. I honestly can't remember. A little bit more going on. Oh, do we need both of these? Well, the key thing is step 1. Step 1. If 4x minus 1 has absolute value less than 9, 4x minus 1, what can you say about it?
It's less than 9 but greater than negative 9?
It represents a number that's within 9 units, less than 9 units away from 0, so it's got to be between negative 9 and 9. We'll come back to this one, but what about if the absolute value of 7 minus 3x is less than or equal to 23? What numbers have absolute value less than or equal to 23? From negative 23 to positive 23. That's where 7 minus 3x has to end up. So 7 minus 3x has to be between negative 23 and positive 23 if it's going to make this happen. And we have the or equal to bar. We can solve each of these. This is from a previous section, 3-part inequalities. We do the same thing to all 3 parts to try to isolate the variable in the middle. So add 1 to all 3 parts, and this will give us the x term in the middle. Negative 8 is less than 4x, and that's less than 10. Need a fresh copy of that 4x. So fresh copy of everything, negative 8, 4x, 10. And we know we have 4x in the middle. We know we need x in the middle. So divide all 3 parts by 4. Reverse the inequality symbols or leave them alone. Leave them alone. 4 is positive. When we divide everything, both sides, all 3 parts, by something positive, we leave them alone. Negative 2 is less than x. X is less than 10/4, 5 halves. Probably what Alex wants. 2.5 would be fine as far as I'm concerned. and write it in interval notation. -2 to 5 halves. The other one, more of the same, except when we divide all parts by -3. Let's subtract 7, subtract 7, subtract 7. -30 is less than or equal to -3x, which in turn must be less than or equal to 16. Yeah, 16. Now we know we want to divide all three parts by -3, so let's write a fresh copy of that -30, a fresh copy of the -3x, a fresh copy of the 16. Divide them all by -3, and then ask ourselves, leave the inequality symbols alone or reverse them? Reverse them. Because we're dividing each part by a negative number. That causes us to have to reverse them. So 10 is greater than, greater than or equal to, x is greater than or equal to -16/3. Now, one additional step you might want to write before you put this in interval notation, you might want to take the -16/3 and put it on the left and reverse the inequality symbols. Not because we're dividing by anything negative, it's just that it's an equivalent statement, but we're ordering the numbers from left to right in the order in which they appear on the number line. The statement x is greater than or equal to -16/3 is equivalent to the statement -16/3 is less than or equal to x, and 10 is greater than or equal to x is equivalent to x is less than or equal to 10. So it's the same interval, just written a little differently, so that when we translate it to the interval notation, the -16/3 goes on the left and the 10 goes on the right. It should be that way anyway. It's just that if it matches the order in which we see it in our inequality notation, maybe it's less likely to make a mistake. But if you want to go instead directly from here to here, that's fine. Skip the intermediate step. You really don't need this if that's troublesome. College algebra students find that step to be a little troublesome in the past, and if you don't like that, don't even write it down. Just go directly to the interval notation. Other case, if the absolute value is greater, I'm going to go directly to the C parts here. C and D parts of, well, no, better not. Nope. The B part is kind of important, and the A part won't hurt. Try to push those off the screen. Absolute value of x is greater than 7. What can you say about x if its absolute value is greater than 7? It could be that x is greater than 7, or it could be that x is less than -7. These are the two possibilities. If the absolute value is greater than 7, just think, it's more than 7 units away from 0, more than 7 units to the right, or more than 7 units to the left. And so you write it using interval notation, union 7 to positive infinity. All right, somebody pick a number from -infinity to positive infinity.
0.
0? The 0, what's the absolute value of 0? 0. Is that greater than -7? Yes. Someone pick another number from -infinity to positive infinity. 100. What's the absolute value of 100? 100. Is that greater than -7? All right. Someone think of a number whose absolute value is not greater than -7. So -8. Take the absolute value of -8. That's 8. Is that greater than -7? Yes, the absolute value of -8 is greater than -7. What's a number whose absolute value is not greater than -7? -6, -8, +8, +6, million, 0. Every real number has absolute value at least 0, right? And 0 is greater than -7. So every real number has absolute value greater than negative 7. So we just look at it and observe all real numbers make this true.
So do you want that, or are all real numbers fine? You want that?
You could, if you say, well, I'll probably ask for interval notation. If you say all real numbers, I probably wouldn't count that wrong, because I know you're thinking the right thing, and I'll just be happy with that. But negative infinity to positive infinity would be the interval notation way to write this. This probably has to go to the next page. Key first step. Absolute value 4x minus 1 is greater than 9. That can happen one of two ways. Maybe 4x minus 1 is greater than 9. And honestly, if that's all I see, and you successfully come up with what? You add 1, you say 4x is greater than 10, you divide both sides by 4. What does that look like? Divide by 4, you get x is greater than 5 halves. You say 5 halves to positive infinity. That's half of the correct answer, right? Really? No, I've got it on silent. I don't know. That's half of the correct answer, right? Is it half credit?
Sure.
Is it half credit? I'm thinking maybe not, because what it says is the student's not quite sure what to do with those absolute value bars. And that's why this problem's on the test, to try to decide, does the student really know what to do with those absolute value bars? So, for full credit, for maybe any credit at all, you want to say 4x minus 1 could also be less than negative 9, right? Two ways a quantity can have absolute value greater than 9. It can be greater than 9, or it can be less than negative 9. Negative 10, negative 11, negative 12, negative 13, all those have absolute value greater than 9. So we do those, add 1, 4x is less than negative 8, divide both sides by 4, 4 is positive. We do not reverse the direction of the inequality symbol. I did that quickly. Did I do it correctly? I think so. So x could be less than negative 2, which would mean it could be in the interval from negative infinity to negative 2. And that's the other half of the solution set. But if you have one of these but not the other, I don't know that that's as much as half credit. It might be some credit, maybe 1 point out of 3 or 2 points out of 6, however it works out. There are 15 problems on the test, so I'm thinking about 6 points apiece with, I don't know, 10 points for your name or something like that. But I don't know, if you don't show the negative infinity to negative 2, or this statement,
so we'll
probably minus 4 there.
When
Yes.
we put it in or, we have to do the negative after the greater than or less than.
This negative right there?
Yes.
Yes. Yes. That's key here. And one more, just for good measure. 7 minus 3x has an absolute value greater than or equal to 23. Two different ways that could happen. 7 minus 3x could actually be greater than or equal to 23. 23, 24, 25, 26, these numbers have absolute value greater than or equal to 23. But what other numbers have absolute value greater than or equal to 23? Negative 23, negative 24, negative 25, negative 26. They're all 23 units or more away from 0. When you think about it, they're there. So 7 minus 3x could be one of those, negative 25, negative 26, negative 27, and have absolute value greater than or equal to 23. So subtract 7, negative 3x is less than or equal to negative 30. Divide both sides by negative 3. Reverse the direction of the inequality symbol. X might be greater than or equal to 10. Subtract 7, negative 3x is greater than or equal to 16. Divide both sides by negative 3. Reverse the direction of the inequality symbol. And x could be less than or equal to negative 16 thirds. And that would also work. I think what I would do, we've got the or, that it comes really all the way down. I would say negative infinity to negative 16/3, because that's the interval that shows up on the left, from negative infinity up to negative 16/3, union, and then this one over here, 10 to positive infinity. If you reverse those two intervals at the bottom and put the 10 to infinity on the left and the negative infinity to negative 16/3 on the right, that would be full credit. That means the same thing. Doesn't matter the order in which you write those intervals in the union notation, but it's probably better if the interval that appears to the left on the number line actually appears to the left when you write it down. It's just a little bit better, better form, I think.